Hi everyone, we'll be solving today the questions from the homework 6. So let's start with the first one. I'll solve the second part of this question. So we're given this vector function. And so we see that the first component, x, is given like sinus pi t, and the second one y equals to t, and the third one z equals to cosinus pi t. So if we fix the second component, so if we fix t or y, we see that we have x squared plus z squared equals to 1, which is the circle whose center is the origin and the radius is 1. So when we fix the second component, we have a circle. So we have a shape of this form. Now, if you look at t, when t is positive and increasing, we see that each value on this circle will be lifted to the right, right? So each point, when t is positive and increasing, each point will be lifted to the right, so which is given of this form. And also when t is negative and when it's decreasing, then each value on this circle will be lifted to the left. So it will continue like this. Thus, the graph that we're looking for is this. Okay? When t is fixed, we had a circle. When t is increasing, then our shape will be lifted to the right. And when it's increasing, when it's decreasing, our shape, the values on the circle, will be lifted to the left. So let's clear all and pass to the second question. Now, we're given the curve r of t. Okay, we want to find, and the parabolate, of course, we want to find the intersection points of the curve and this parabolate. So we're given r of t as in this form, the multiples of I and k. We can write it like this too, right? Of this form. So the multiple of I gives us the first component, okay? And the multiple of j, if we had j there, then its multiple will be given us the second component, and the multiple of k gives us the third component. Then we have x equals to t, the first component, and y equals to 0, and z equals to 2t minus t squared. Now, as we want to find the intersection point, then it means this point is both on the parabolate and the curve. Then it should be satisfying both of the equations. So let's plug these equations of x, y, and z into this parabolate. Now we have z equals to 2t minus t squared. We have 2t minus t squared to the 2 as in this equation. And as x equals to t, we have t squared plus y squared, which is 0. So we have this equation. And if we solve that, we obtain this t squared times this parenthesis equals to 0. So it means t is either 0 or this parenthesis is 0, which is exactly this, right? Then it means t is either 3 or 1. So we have 3 values of t. Thus the intersection points are when t equals to 0, we get 0, 0, 0. How do we get it? We plug here into r, into the function r, and obtain 0, 0, 0. When t equals to 0, we get 0, 0, and 0. And when t equals to 3, we get 3, 0, and minus 3. And when t equals to 1, we get this point, this vector, 1, 0, 1. So these points are on both the curve and the parabola. So these are the intersection points. Now let's pass to the third question. Now we're given the curve with parametric equations where x equals to t squared, y equals to 1 minus 3t, and z equals to 1 plus t to the 3. We want to show that these two points are on the curve, but not this point. So it's easy to see that when t equals to minus 1, we get this point, and when t equals to 3, we get that. How do we do that? If you so if x equals to 1, then t should be either minus 1 or 1. And you try for t equals to minus 1 and get y equals to 4, right? And again, for that one, z equals to 0. So you get this point when t equals to 1. And if you do that for the second point here, so if we do the same things actually, if t equals, so let's start with that. So if x equals to 9, then t equals to either 3 or minus 3. So you check for the other values for the other components. So if you try t equals to 3, you get in the second component minus 8 by using this equation. And by using that, you obtain the third one, 28. So you see that when t equals to 3, you get this point. So as we found the values of t's for these points, which means these points are on the curve. Now let's show that this is not on the curve. Suppose that it is. Now then for some t in real numbers, we should have these three equations, okay? Because as we suppose that this point is lying on the curve, then for some t we need to have these. y4, because the first component of the given point is 4, and the second one is 7, and the third one is minus 6. So by using the second equation, we obtain that t equals to minus 2. And if we plug t equals to minus 2 into the third equation, we get minus 7 instead of minus 6. Which means that this point, 4, 7, minus 6, is not lying on the curve. So we're done with this problem. Now let's skip to the fourth one. Okay. We'll solve the second part of this question. Now we want to find a vector function which represents the intersection of the two surfaces. We're given a paraboloid and a cylinder, okay? Now we want to find the intersection to write an equation of a vector function. Now, how do we find the intersection of these two surfaces? So we see that y equals to x squared, then we should plug that into this equation of z, okay? So z equals to 4x squared, and as y equals to x squared, we get x to the 4. Now we have an equation of z in terms of only x, and y is also given as a function in terms of only x. So it's easy to start with x, start with saying that x equals to t to parameterize, because it will be easier because z and y are the functions in terms of only x. So if we say x equals to t, then y equals to t squared from this equation, and z equals to 4t squared plus t to the 4, because as I said before, as we did before, we know this equation. So we have the parametric equations of the given of the desired curve, desired vector function, which is this r of t, where the first component of this function is t, as we said, x equals to t, and the second one is t squared from this, and the third one is this. So this is the vector function, which represents the intersection of the given two surfaces. Now, fifth question. Now we're given two curves. One of them is u of t, and the second one is v of s. We want to find the intersection points of these two curves. So we need to, again, equalize each of the components. So we equalize them component-wise, okay, to find the intersection point. So first one, t, first component of the first curve is t, and the second curve's first component is 3 minus s. So we have this equation. Then 1 minus t should be equal to s minus 2. And finally, we have 3 plus t squared equals to s squared. So we have these three equations. So first and the second equations give us the same equation. That's why we'll try with this, the third one. So we have this equation. Now, as we know from the first one that t equals to 3 minus s, we just plug this equality into that equation and get s equals to 2 by solving. It's easy. By solving these equations, we obtain s equals to 2. As s equals to 2, if we plug this into the given curve, which is v of s, because it's in terms of s, so v of 2 will give us the intersection point. So when we plug s equals to 2, we'll obtain this point 1, 0, 4, right? 3 minus 2, 2 minus 2, and 2 to the 2 squared. So we have this point, which is the intersection point. You don't have to find t specifically, but if you want, you can find first. You can find first t, then you plug that into into the first curve to get the point, the intersection. You'll get the same intersection point, obviously. So the last question. Okay, we'll solve the first and the third part of this question. We want to match the given vector fields with the plots, okay? Now, we have this vector field. So f of x, y is given of this form, x, comma, minus y. So let's sketch first the coordinate system, okay? Sorry. Okay, now, so it's logical if we start with the ones, so with the axes or lines that we know well. So we started with the y-axis. We want to find the change through this axis, okay? So if when we're on the y-axis, okay, this is the y-axis, when x equals to 0, we obtain these vectors. So for example, if y equals to 1, then we get the vector 0 minus 1, which seems like this, right? So when y is positive, we obtained a vector which is downwards. So if we had y equals to 2, we'll be obtained 0 minus 2, so it will be again downwards when y is positive. So when y is negative, when y equals to minus 1, we obtain this vector, which is 0, 1. When y equals to minus 1, we have the vector 0, 1, which is now upwards. So when y is negative, we obtain the vectors which are upwards, yes. And we do the same things for this one too. So when we're on x-axis, okay, which means when y equals to 0, we obtain the vectors x, 0. So let's write them too. So for any x, we obtain these vectors. So when x equals to, for example, 1, we have the vector 1, 0. It seems like this. When we have x equals to -1, we have this, right? For any value of x, our vectors will be like this. So let's find that between these 4 plots. So now you see that, so I know the answer, that's why I'm passing there. So we see that when y equals to, actually when y is greater than 0, we have the vectors downwards, okay, as you see here. And when y is less than 0, we see that our vectors will be upwards, as in here. And along the x-axis, so I made a mistake there. When, for example, when x equals to, for example, -1, then our vector will be -1, 0. So it will be like this, right? So they will be like this. When x is negative, we'll have vectors which seem like this. And when x is positive, they will be like this. So exactly what do we have? What we have here and here. So we did that before. So the answer for the first part is 4, the plot 4. Let's do that for the third part of this question. Now we have this curve, f of xy equals to y, y plus 2. Now we plug y equals to 0 and get the vector 0, 2, right? Let's write that. This is not important. Let's first write the coordinate system. Okay, now along the x-axis, we know we have the constant vector, the same vector all the time. Okay, let's write that. So along the x-axis, we'll have the vectors 0, 2, where x equals to 0 and y equals to 2, right? For any value of x, it doesn't matter if it's less than 0 or greater than 0. Now we'll have something like this, okay, for any value of, sorry, I cannot write it, but you get that. So when, let's look at now that part. When y equals to -2, we have -2, 0, the vector -2, 0. So this is obviously the line y equals to 2, right? Let's write first that line. So when y equals to -2, suppose that this is -2, okay, we have this line, actually the same with this. It says us that we're on this line, y equals to 2. So our vectors will be like -2, 0, all the time, the same vectors along this axis, right? So let's draw them. So -2, 0, the vector -2, 0 is something like this. So along this axis, this line, sorry, we have these vectors. Okay, no matter what the variable x gets. So let's find the plots. Now, if you look at this, the first one, we see that along the y equals to -2, the line y equals to -2, we have exactly the same vectors. And along the x-axis, we have the vectors. What were they? They were 0, 2, right? The vector 0, 2, right? All the same. They are the same vectors always. The length of the vectors are the same through this line. So the answer is the first plot for the third part of this question, 4C. So that's it. I hope you understand.